All right, so hi everyone. I'm excited to have Professor Gabriel Estrada talk in our seminar today. He is a professor of computer science at University of Bucharest, where he recently moved from the West University of Timișoara in Romania. He graduated from University of Rochester in 1999, and he was a postdoc and a technical staff member of the Los Alamos National Laboratory. And his interests are very broad. He's interested in social simulation, game theory, multi-agent systems, discrete and complex systems, modeling social dynamics, and more. Today he'll be talking about mechanism design with predictions for obnoxious facility location. I love the title. And this is joint work with Cosmin Bronkish. And yeah, Gabriel is a friend and a collaborator, and we organized together a workshop. So I'm very happy to have him here. Welcome, Gabriel.
Thank you, Elena. Thanks everyone for being here. Good morning, I guess. You've seen the title. I'm going to talk about some work that basically, frankly, is not refereed yet. It's been submitted, and I'm waiting for a rebuttal like next week, but it's not yet, refereed, and I haven't put it yet on archive. Also, I have to caution you that for me, this type of interest is kind of recent. I started thinking about this type of problem this summer, basically, and I would call it recent ongoing work, which is a more polite way of saying it's half-baked in ways. So I won't give you a lot of all of the technical details. I want to give you a flavor of what the results and the issues are, rather than full details and proof, and there are a lot of things that I will skip. And hopefully there are some interesting open questions for you. If you want to work, I can send you the paper offline, and we can talk about that. So this picture is related to a riddle that I've known since I was basically in high school. I was a member of the extended Romanian team that was selecting the 6 people from Math Olympiads, and we would trade funny problems. And this one I've known since 1986. So a city is so small that all pubs are on a single street, which is a straight line. By the way, the picture on the left, I'm sorry, it's not as relevant in an American context as it would be in Germany, where I gave this talk like 10 days ago.
West Lafayette is just like that.
Okay. For the record, this is Beer König. It's a pub in Mallorca, Spain, where a lot of the German tourists come, and there is a single street called Schinkenstrasse in slang, and so I thought it's fitting. So anyway, there are a number of pubs on a single street, which is a straight line, and you have an odd number of friends. They're on the street, and all of them are in pubs, not necessarily in the same pub. Maybe one is in pub A, 2 more are in pub B, and so forth. The issue is that there is an odd number of them, and they all have, whatever social media you want, and they realize, okay, we're on the same street, let's meet. But they're computer scientists, so let's meet in a point where the total distance we travel is minimized. And the problem asked to prove that they meet in a pub. Okay. Maybe I would give you a couple of seconds. It's quite easy, actually. Can anyone guess a solution to this problem?
Can they meet in the mean?
The median.
Yeah, the median, exactly. So the point is, you take one from the left and one from the right, and they have to travel at least their distance. And then there is a guy in the middle, the median guy, who doesn't move. Hence, they meet in a pub. as the problem was asking, so that's a problem. Okay, I'll come back to this problem a little bit later. So the context of this work has to do with something that I've seen that Elena has done recently, and hopefully a couple of you are familiar with. And this is the area of algorithms with predictions. And as far as I'm concerned, this is probably the hottest direction in algorithmics recently. And there is this beautiful book by Tim Ravgarden and a chapter by Michael Mitzemacher in this book. And the notion of algorithms with predictions is based on the idea that often when you want to optimize something, you might have some sort of predictor for the solution. And you would want algorithms that take advantage of this predictor in a way that it would improve upon ordinary algorithms. So, if there were still phone books in this world, you wouldn't look for a name in a phone book by doing binary search. You would predict where the name is in the book, and maybe your prediction was wrong. Maybe your prediction would be right. But in any case, if your prediction is right, then you would find the name in the book much faster than with binary search. So that's a context of supplementing algorithms with predictions, often coming from machine learning. And there is a vibrant community in the webpage where there essentially most of the papers in this area, I guess. And this paper will hopefully be there in a couple of weeks or so. And what do we want when we're talking about an algorithm with predictions? So there's a classical framework due to a bunch of people at NeurIPS a couple of years ago. And they were talking about two measures, essentially: consistency, how good your algorithm is when the predictor is perfect, and then robustness. What happens, how does the quality of the algorithm degrade when your prediction is really, really bad? And normally, in this type of setting, you can get one or the other. There is some sort of trade-off between consistency and robustness. So the more consistent an algorithm is, typically the less robust it would be, or something like that. So at least in a couple of contexts, this is what's happening, is that robustness will blow off the moment when you say you trust the prediction. One extreme is you don't care about the prediction at all and you just run a worst case algorithm. And the other extreme is that you just return the prediction, whatever that is. And that's good if your predictor is perfect, but that may be really bad, if your predictor is bad. So we want trade-offs between consistency and robustness. And just to make this a little bit more formal, let me take a measure of algorithm performance on an input C in the presence of a prediction P sub C. And P sub C is an approximation of an optimum point of some sort. And we measure the distance between P sub C and the optimum. And we're looking at essentially the worst possible performance of the algorithm, say approximation ratio or competitive ratio, it's about, if it is about online algorithms, for settings where the difference between the optimum and the predicted point is at most eta, as a parameter of eta. And an algorithm is called alpha consistent if the performance is at most alpha, when the predictor predicts the optimum point. Okay. And the algorithm is beta robust if essentially for all etas you can get much worse than beta. Okay, that's the definition that comes from this NeurIPS paper, 2018. Actually, Zoya Svitkina was a summer student when I was at Los Alamos, so I've read this paper, with great pleasure, and I do recommend if you haven't seen it. It's a very cute little paper and very simple, but as far as I'm concerned, a very elegant framework. Let me ask because I would assume there are students here. Any questions so far? Okay.
I'm just curious. You define eta as d of p sub c comma y star sub, but in C of eta, you have such that d of this is less than or equal to eta. When would that become less?
I mean, I would. Yeah. I'm overloading. I'm overloading meaning here. In the equation about C, eta is a parameter, essentially. Sorry. Yeah, it's totally true that eta would be a parameter, and I would just make it at most eta. Yeah, so you're totally
sorry. Yeah, my bad. I didn't.
Yeah, no. It's a perfectly valid point, and I should haven't had that eta for the distance, but my thought process was that that's basically what we're parameterizing. We're parameterizing this function C by the distance between the predictor and the optimum. And the function C basically measures the worst performance of an algorithm, whatever that is, approximation ratio or competitive ratio. I'm going to be a little bit sloppy when it comes to notation, so forth. I'm going to even use this as a substitute for like social welfare, but it wouldn't apply to this definition. But anyway, the point is, I want, of all configurations at distance at most, where the predictor is wrong by at most eta, what's the worst I can do?
Okay, that makes sense. Thank you.
That's the point. So yet more context, and this is about algorithmic mechanism design, and I'm pretty sure that a lot of you, a significant fraction of you, have seen this book. So the setting here, I mean, I'm probably repeating this to people that already know it, is we have n agents, and let's just make the whole thing into the setting where these n agents want to jointly compute a function f, which depends on private information that the agents may have. So xi is the private information of agent I. And now agent I is may be self-interested to get a value of f he or she wants. So it may lie, it may tell a different value than xi, in order to get some favorable outcome. And what we want in mechanism design is we want an algorithm, a mechanism to compute this function so that no agent or coalition of agents gains by lying. Okay, so the mechanism will make it in the interest of every player to basically report its information truthfully. So let me give you one example. And this is why I brought up that bar meeting problem, because I had known it since, for a long time. And then I'm reading theoretical computer science, and I'm seeing this pretty classical paper by Ariel Procacci and Moshe Tenenholz on approximate mechanism design without money. And here is a problem that I knew since 1986. So now imagine that the agents may lie about their location, and they might try to misreport their location in order so that they travel less, so that they, as a result of the protocol, they travel less. In fact, this doesn't happen. Procacci and Tenenholz show that for this facility location problem, this median mechanism is what's known as group strategy proof. That is, not only one agent cannot benefit by lying, but it's not even true that a coalition of agents could all benefit by coordinating their lies. Okay, so the median mechanism is what's known as group strategy proof. And of course, for the objective function, which is the sum of distances, then it will compute the optimum. But you might want to have different optimum functions. For instance, you might want to minimize the largest distance traveled by a single agent. And for some other objective functions, essentially, you can prove that no strategy proof mechanism can find the optimum. And in several cases in this paper, essentially the median mechanism, the one that we've seen, agents report their locations, and then you choose the median location of the reported locations. This provides the best approximation mechanism. So this is proved in this paper. Okay, so the mechanism here is precisely this one. Agents self-report their locations, and we choose the median. And for some objective functions, this is the best one can do, as long as we want strategy-proof protocols. Okay. Now, to be really honest, I wanted to do work in algorithms with prediction, and I wanted to do work in algorithms with design. So I thought this summer, why not try to merge the two, do mechanism design with predictions? And then I looked into the literature, and to my chagrin, it had already been done this year at IJCAI 2022 by these two gentlemen. Moreover, there was a paper at EC precisely this summer where they took up this framework of mechanism design with predictions, and they applied it to the bar meeting problem under various objective functions. So here the idea would be the following: you are the designer of the protocol. You may have an estimate of the actual value of the function that you want to compute, and that may help you in creating a protocol that's better than a protocol that doesn't have this information. That's sort of the very rough idea. Now, since I saw that there was already work in this direction, the obvious thing to do if you want to, to try your hand at mechanism design and at algorithms with prediction is take another problem and see what you can get. And this is what I'm doing in this paper. I'm looking at mechanism design with predictions for a different facility location problem, and I'm going to be a little bit more precise in a little bit. But essentially, you have n agents in a metric space, and you want to choose one bad facility, something that everyone doesn't want in its neighborhood. So agents want to be far from this facility. Think of, I don't know, a nuclear power plant or whatever. And without predictions, this is a problem that's been studied already. And there is a conference paper in 2011 and a journal paper which extends this work in 2013. So this is what I'm doing. I'm giving algorithms with prediction for the obnoxious facility location problem. And if you remember, what I said is you want a trade-off between robustness and consistency. In other words, you want a family of protocols which interpolates somehow between purely doing the worst case algorithm, which doesn't care at all about predictions, and the the algorithm that simply follows the prediction, whatever it may be. So I'm giving a family of protocols parameterized by lambda, where lambda equals 0 is basically an approximation algorithm that has no prediction at all, doesn't care about prediction at all. And lambda is 1 is what's happening when you follow the prediction blindly. And as you can see, yes.
Sorry to interrupt. So how do we think about predictions here? Like each facility, whatever, we have the distances and locations. And what is predicted here? What can they use?
No, it's not the agents that get predictions. it's the mechanism designer that gets a prediction. And the mechanism designer gets a prediction on the actual location, on the actual optimal location of the facility, should all agents report truthfully their locations.
Okay, so you kind of run the initial protocol without predictions, I mean in advance, and so you get some estimate of that location.
No, you get an estimate of the location as a designer.
Okay,
So
okay, yeah,
sort of,
that's the, yeah, it's not
maybe you do some sort of like statistical survey on the population, and they tell you kind of where you don't know where everyone lives, but you kind of know statistically, and then you have a good idea as to something like that. So it's the designer of the protocol that gets a prediction, not the agents themselves.
Okay, so some like kind of like ball of some radius where the location should be.
Actually, a point. You get a point.
Okay, a point. I see.
You get a point. I'm going to be a little bit more specific, but I wanted to like discuss results and tell you what I'm doing informally before I get a little bit more formal. So the designer gets a point in this metric space, and I have a couple of metric spaces. And the news here is that for segments, for squares, for circles, and for trees, the trade-off is the same. I get the same trade-off in all these cases. Okay, and you can see it depends on lambda, as robustness is 3 plus lambda over 1 minus lambda, and it blows off as lambda goes to 1, of course. The algorithm is really bad, really non-robust. Whereas consistency, which measures how good you're doing, if your prediction is perfect, goes down from basically 3 to 1. So the closer to a 1 you are with parameter lambda, the better you do if your prediction is perfect, but the less robust your algorithm is. Okay? And I should point out that the case of squares was not studied before, even in a setting without predictions. The other ones were studied, and essentially the three, the primary three here for robustness and consistency is basically that there is a 3 approximation algorithm for the problem in the setting without predictions. Okay, so I get the same trade-off for a bunch of spaces, including one where this was not studied before. There is the same trade-off essentially happens when agents have dual preferences. There are 2 types of agents. Some of the agents want to be far from the facility. Some of the agents want to be close, and their utility function reflects that. And there is a formal framework of Zhu and Li in AMAS 2015, and I'm using that one, and I'm extending that to to the setting with predictions. Okay, so and there are, as you can see, the title of the slides is the good. I'm talking here about the good part. Okay, and then I can prove essentially that for segments, this trade-off is optimal. And I'll put a more precise result, but the point is that if you choose any value of the consistency on this plot between 1 and 3, then essentially you cannot do better with robustness. Okay, that's the story. So for segments, you can prove that this trade-off is the best we can do. Okay. Other questions?
Oh, sorry, what does it mean for segments?
Segments. So I have points on a 0, 1.
On a line, okay.
Actually, a segment on a line, not the whole line. Because on a whole line, the farthest point would be at minus infinity or so, something. So I need to have some sort of complex space in order for this to make sense.
Yeah.
So for circles, you would need two coordinates, right? How does
No, it's not a disk, it's a circle. Points are on the frontier of the disk. And you measure
they're like
distance.
around the football, around the like a circle.
Yes,
Okay, I see.
around the circle. And you measure the distance basically on the circle. The distance, you have two arcs on the circle, and you take the, or if you want.
So this is all one-dimensional. Okay. In some sense, even like with the squares, you mean that the points are on a square? They're not in the interior of the.
No, the points may be in the interior. There.
Okay.
So it's not one-dimensional.
Okay.
But if it's two-dimensional, won't you need two parameters, like one lambda and something else too?
No, lambda is a parameter that measures roughly how confident you are in the quality of your predictor.
Oh, sorry. So
how closely you're going to follow the predictor. It's not about anything about the predictor per se. It's about how much trust you put in the quality of that, and how do you sacrifice prediction versus for robustness, essentially.
I see. Sorry, that clears it.
Mm-hmm. And in fact, this is something that I was talking about the previous paper by Zoya Svitkina and Ravi Kumar and Purohit. So they basically have something like this. They have they were doing ski rental, and they have a family of algorithms with parameter lambda, and the same type of trade-off between robustness and consistency happens there, where what you measure there is the competitive ratio. Okay.
Right. I understood the trade-off and why it happens. It just didn't register for me that lambda is a parameter for confidence. Thank you. It makes sense now.
Okay. Actually, it will be clear in a second because I want to be more specific. But anyway, the point is that at least for segments, and frankly, it should be true for circle and trees probably as well, but I haven't really had the time to to check that. This is the best, it's optimal trade-off. You cannot get a more robust algorithm if you want your consistency be in a certain at a certain level. So here is a little bit more formal. You have n agents in a metric space, and you have a configuration C consisting of their reported locations. As I said, the agent locations are private information, and the utility of choosing a point Y depends on the actual location. Actually, I should have put here a star for the true location of the agent. So it's simply the distance between the true location and the point that gets chosen. And the goal of the protocol is to choose one point in a space that maximizes the sum of distances between this point and all the points in the metric space. Okay, so when I'm talking about the segment, I mean that points are located in the interval 0, 1. When I'm talking about a square, I have n points that are in the 0, 1 times 0, 1 square. And I could, of course, play this game on k dimensions, but I don't have results for k greater than 2. When I'm talking about trees, and this could be played in graphs, essentially I'm thinking of the following scenario. Edges are basically embedded as segments in some, n-dimensional real space. And then, at least for trees, there is a well-defined distance then between 2 points on a tree. So I'm not talking about a tree as a graph theoretic concept. I'm talking about a tree as a, as a set in this sense. And it probably doesn't matter the fact that I said here segments, but you could play this game with some sort of rectifiable curve or something, but for now, let me just take this. Now, what is it that I'm looking for? I'm looking for a mechanism with prediction. And for my setting, a mechanism with prediction, and the deterministic one, is a function that takes an n-tuple of self-reported locations, so an n-tuple from x to the n, and then it takes a value which is normally another point in x, but you will see that it may make sense to actually have it as an element in a smaller subset of x. Maybe not every point in the space is a good prediction, and returns a point in x. And a mechanism, a function like this, is group strategy proof if for every coalition S of agents, for every input configuration, for every prediction, the agents in S basically cannot coordinately change their locations and all strictly improve their utility. There is at least one of them that does not gain by misreporting their location in this coordinated fashion. Okay, so it's stronger than just strategy proofness, because it's about also groups not being able to coordinate. Okay, and to make things a little bit clear, here is a mechanism that was given on segments. So this is a setting without predictions that I was talking about. I have endpoints, and I'm essentially going to vote. I'm going to divide my segment into the first half and the second half. And essentially the points in the first half between 0 and 1 or 2 should vote to have their facility at 1 at the other end, because it's the farthest. Whereas points in the second interval should vote for 0. And the mechanism states that if one votes win against 2 votes, then you return 1, and otherwise you return 0. So this is what they proposed. This is group strategy proof. It's a 3 approximation algorithm for the optimum for this problem. And it was proved later that there is no strategy proof mechanism that gives an approximation ratio strictly less than 3. Okay, so but is this mechanism clear? Okay, you have endpoints, and each point chooses whether to vote for one endpoint or the other endpoint. It's actually very easy to see that the maximum distance is going to, it doesn't pay to report some point in the middle. If you want the sum of distances to be as large as possible, then you'd better report one of the endpoints. And now the question is, which one? Should it be 1 or 0? And this mechanism basically achieves the optimum approximation ratio in the case without predictions. So this is a baseline for the scenario for the point lambda equals 0 on this graph. Okay, so lambda equals 0 is a case without predictions. You have a 3 approximation, and that's optimal. Okay, so here is what I'm doing for segments and for squares. And it's basically very simple, and it's basically the first thing you would think of, probably. If you want to favor your predicted point, so now you get with your configuration, you also get a prediction of where this optimum point is. And more precisely, you're going to get a prediction at one of the corners of the hypercube. You're not going to get a prediction in the middle. In a certain sense, this is reasonable because as I said, you can prove that the optimum is going to be reached at a corner. So then it's reasonable to assume that the predictor will not predict, something where you cannot get the optimum. Okay, so you're going to get a prediction of a corner. And now what I'm going to do a voting mechanism on coordinates. So on each coordinate, basically I project. And I almost do the same mechanism as before. But because I want to somehow favor the predicted point, I'm going to add lambda n extra votes for the coordinate of the predicted point on the, on that coordinate voting mechanism. So essentially, I'm choosing the x coordinate of the predicted point and the y coordinate of the predicted point independently by looking at the x coordinates and the y coordinates and running the previous protocol with this extra addition that I'm adding lambda n votes for, and yes, it's fractional, but doesn't matter, lambda n votes for the coordinate of the predicted point. Okay, so this is the mechanism with predictions that I'm using for segments and squares. And something like this happens in other cases as well. I don't have time to discuss the circle, but then essentially you're going to either return the predicted point or its diametrically opposed point, and you're going to somehow vote for one of them, and points that are closer to the predicted point are going to vote for the other one, and points that are closer to the diametrically opposed are going to vote for the predicted point. And then you're going to do this lambda n extra votes in order to get predictions that are, to get algorithms that will take predictions more into account. Of course, if lambda is 1, then by bringing n votes to the table for the predicted point, you're totally winning. It doesn't matter what the other ones are doing, you're going to make the predicted point win. So that's a mechanism with predictions that I'm using for segments and squares. And here is the result for squares. And it's basically 3 plus lambda over 1 minus lambda robust. And it's in the sense of an approximation ratio. I'm looking at the social welfare of the optimal solution and the social welfare of the solution provided by the algorithm. And it's no worse than this ratio. Okay, that's a robustness component. And consistency is almost the same, except that now I know that the predicted point is the optimal point. Okay, so when the predicted point is the optimal point, in all such settings, the algorithm will be no worse than 3 minus lambda over 1 plus lambda. Okay, so I had these two parameters, robustness and consistency, and you get the trade-off that I was describing before. And the idea of proving, so for every scenario, segment, square, circle, trees, I have to prove 2 results about approximation ratios, one for robustness, one for consistency. But there is a single idea that kind of goes on in various different forms in all these proofs. And sort of the idea is the following. I'm going to take a configuration C, and I'm going to create another configuration C1, which is in a certain sense of the same type as far as the voting algorithm is concerned as C. And I would almost want to say that the approximation ratio of the algorithm on C is at most the approximation ratio of the algorithm on C1. And that one I can handle with for robustness and consistency, as needed. In reality, it's not really the approximation ratio. It's something a little bit trickier because I'm comparing the social welfare of the optimum point for C on configuration C1 versus the social welfare of the point given by the algorithm on configuration C1. And that's a ratio that I want to bound my performance of the algorithm. So here, ACPC is basically the social welfare of the point that is given by the algorithm, on configuration C. It's a sum of distances of all points in C to this point given by the algorithm. And then if I have C1, I can handle the second part easier, proving that the upper bounds that depend on lambda, that's not really a problem. So here is what I'm doing. Let me take a configuration like this square, and I'm going to assume, for instance, that the algorithm tells me that I'm going to return point D, which means that N1 plus N2, and here also, in this case that I'm showing, I'm sure also the predictor is at D, but doesn't matter. All the other cases work the same. It's only for illustration of what's going on. So it means that on X coordinates, I'm comparing N1 plus N2 against N3 plus N4 without prediction. And on Y coordinate, I'm comparing N2 plus N3 against N1 plus N4. And who's winning gives me the coordinate. And in this case, the fact that the algorithm returns D, it means that 1 wins on both X coordinate and Y coordinate. So what do I mean by configuration C1 of the same type as the configuration C? So C is an arbitrary configuration which has N1 points in the square CTRU and so forth. I count how many points are in that, and I have to be a little bit careful to say how do I count borders, but that's easy to do. Okay, so C1 does the following. I'm going to take all the points in one of those squares, and I'm going to move them as close to the predicted point as possible. For instance, if the predicted point is D, then all the points in the rectangle CTRU are going to be moved to T, because T is the closest point that I can have in that square. That minimizes the distance to D. And the same thing happens for the other rectangles. For the other squares, I move N2 points to R, I move N3 points to S, and then finally, I move all N4 points to D itself, because, okay, so that's a worst case configuration. Now, when it comes to counting votes, this configuration is totally similar to the configuration C. So the algorithm on C1 will produce exactly the same result as it produces on C. That's what I mean by the fact that it's a configuration of the same type as C. And now, if you remember, I wanted to compare these two ratios. And what I'm going to try is I'm going to try to get the numerator right by essentially subtracting from both terms in the approximation ratio the same quantity in such a way that when I make the computation, the numerator gets the right value. And that quantity is positive because I'm moving points closer to the predicted point. So in a certain sense, the social welfare, which is the sum of distances, will be smaller for the configuration C1 than for a configuration C, because points are closer to D in C1 than they are to D than they are in C. That's just trivial. Okay, so the fact that that is a non-negative number is easy. And now if you do something like 5 divided by 3 and you compare it with 4 divided by 2, of course 4 divided by 2 is larger. So if you subtract the same quantity, the same positive quantity, the fraction is going to increase. Okay, so that's the first step. And then the second step is whatever I have in the denominator, I want to be lower than the ratio that I was talking before. And in order for that, I have this term composed of four quantities, the three quantities in the denominator and the denominator of the right-hand side. And essentially, I want to prove that this quantity delta is greater than 0. That's what I have to show. So that's the general method for all the cases, or many of them, actually not all, but many of the cases that I'm showing, is to have something like this delta and show that delta is greater than 0. And because of that, I'll have the previous inequality true. And then once I have that inequality, coming up with the upper bound is easy because I only have to figure out what's going on the concrete configuration C1 that I talked about before. So that's the easier part. So here is, again, delta, which I have to show that it is greater or equal than 0. And to show that, it's a case-by-case analysis. And as I'll show you in one case, I'll illustrate this. It reduces to a sum of triangle inequalities. So let me show to you this briefly in the case where the optimum point is at B in the square. So I remind you that the predictor is at D and the algorithm gives D, but the optimum is at B. Okay. You may wonder, where do those voting inequalities show up? They show up in the bound, in the 3 minus lambda over 1 plus lambda. That's where they show up. They don't show up in delta. So when you parse that complicated expression above, what you get is an expression which contains the sum of distances from the points xi, the original points, to D, minus the sum of xi to B, plus some terms that are due to this configuration C1 that has points at, well-defined locations. So for instance, if you take a point at T, the distance from T to B is going to be square root of 5 divided by 2, right? So that's why you get those square root of 5s. Now, on this picture, imagine you have diagonals. You also put diagonals. So now you have 8 triangles in this, in these terms. And you want to treat points in triangles and separately, depending on the kind of triangles. Now, some of the triangles are okay because for some points xi, they are simply closer to D than they are, simply farther to D than they are from B. So the difference between the distance of xi to D and the distance from xi to B is greater than 0. Those are easy. But let's take a case where that doesn't happen. Let's take the case where I have, for instance, a triangle CTR. The distance to D is smaller than the distance to B, smaller or equal in those cases. Now, how small can it be? Well, the worst difference I can get is when I choose the point xi to be at T. And that gives me a negative number, which is 1 minus square root of 5 divided by 2. So, because that's a worst case, I get that inequality. And if I sum up all these inequalities, and I take into account the fact that since I have n1 points in the whole rectangle, I have at most n1 points in the triangle CTR, okay, then I get essentially a part of delta which is accounted for by the triangle CTR is greater or equal than 0. Okay, so I've done this for triangle CTR. There are 4 more triangles where this happens. And for the other triangles, the first term is greater than 0 anyway. So I have 8 triangles, 4 are closer to D than are closer to B than to D. And for the other 4, I use this fact that I cannot get worse than, and kind of that's the idea of proving that you get delta greater than 0. And that's the kind of analysis that I do for, actually for both consistency and robustness. In each case, I do an analysis of this sort. Okay, so this is just to illustrate the method, but the arguments are curiously a little bit different. In other cases, for instance, for circle, there is something else that's going on, but the general gist of the method is that I use this configuration C1, which is of the same type as C, and I compare C against C1, and then I use C1 to control the approximation ratio for both consistency and robustness. Questions? Now, let me.
So you're saying that you don't know whether it generalizes to a grid or things like that, or you think it generalizes, but you didn't work out the details.
You mean like in a three-dimensional?
Yeah.
Well, first of all, it becomes more difficult to do this, and I was pretty much doing computations on my own. And there is something that seems to happen at 2, which I'm not sure happens at 3 and more. So there is an inequality between N2 and N4 that is true at in 2 dimensions, but it's not true. I'm not sure something like this is true in higher dimensions. So let me actually, I can explain it on this picture. Let's assume without predictions. So for instance, let's assume that N2 plus N1 is less than N3 plus N4. Okay, that's voting on the X coordinate. And then N2 plus N3 less than N1 plus N4. When I add these two quantities, I get basically that N2 is less than N4. So in 2 dimensions, essentially N1 and N3 cancel because they appear on both sums an equal number of times. But the moment you go to higher dimensions, you're going to get a more complicated situation. And frankly, I haven't worked out. It was also pretty hairy, but I'm also not as confident that this could be made to work. I mean,
so the reason algorithm without prediction that works for grids, for higher dimensional things?
No, it wasn't studied before. I've studied even the case they were, even the case without predictions was not studied for grids.
Okay, I see. So a lot of
I've done the analysis even in this case.
Okay.
Okay. Other questions?
Thanks.
Okay, so I'm going to go quickly over this one, and it might be the most interesting to you, but it's not really that hard, and it's a little bit disappointing. This is a result that tells that essentially for lines, the mechanism that I gave is realizes the best trade-off. You cannot get a better trade-off. And it kind of goes through a characterization of group strategy proof mechanisms without predictions on segments due to Ibaraki and Nagamochi, and there is another work that overlaps and prove the same result. And essentially, you do have some sort of characterization of mechanisms, and then you analyze those mechanisms and you get this lower bound. So it's not terribly interesting for segments. But this is an indication that what I'm doing is, right. Let me go into the parts that are not so good, but still parts that are not that bad. So the mechanism that I just presented to you, the voting mechanism, is not group strategy proof. It is strategy proof, I can prove, but there is a coalition of 2 agents that can defeat it. So here is an example. Imagine that you're in a left situation, and now you have 3 points at that location. The number of points in the blue locations refers to that's the number of points. So 3 plus 1 is 1 plus 3. So imagine that in this scenario, the algorithm will choose 1 because it's the same number of points. It has to choose an endpoint. Now imagine, points that are at 3 are a distance 1/2 from the chosen point. They would rather have a point farther at the opposite end. They would rather choose the lowest point. And for that, they could just misreport their location as, in the corner. And then instead of having, 3-1 versus 1-3, you have 2-1 versus 3-2. And now it's the lowest corner that wins. So you can have 2 points. One will do this on the x coordinate, the other one will do this on the y coordinate. And they can, they can manipulate the mechanism. So it is strategy proof, but not group strategy proof. And I don't know if the previous result is proof for, if the trade-off works for some sort of group strategy proof, because the protocol that I gave is not one. Okay, so that's one bad news. Not that bad, but let's say a little bit. Also, what's happening in the case of dual preferences, and I see that I'm awfully out of time, is that I'm not using group strategy proofness, but a weaker notion. I'm forced to do it. And basically, this notion is that agents cannot improve their utilities by more than a multiplying factor of delta by coordinating their deviations from the truth. So this was the problem by Zhu and Li at AMAS. And you had 2 agents, remember, type 0 agents, they want to be far, just as before. Type 1 agents, they want to be close. And the utility is 1 minus the distance. That's how Zhu and Li defined it. And the mechanism is a little bit different in that first you apply some sort of voting on transform locations, where the transform locations is symmetric for the players of type 1. The agents that want to be close, you take into account the symmetric location with respect to 1/2. That's one change. And the other change is that in voting, you're not taking 0, 1/2 for these transform locations, but 0 to 1 minus lambda divided by 2. And this algorithm is approximately group strategy proof 1 plus lambda over 1 minus lambda, refers to this definition that no coalition can coordinate so that everyone gains at least this much. And again, it's 3 plus lambda robust over 1 minus lambda and 3 minus lambda over 1 plus lambda consistent. And maybe I will skip this because it would get quite long. It's not difficult. Essentially, you prove that the configurations where all points want to be close, that the result holds for these points, and that these configurations are the worst. Configurations where points want to be far have better approximation ratio. That's the setting, the type of proof. Finally, let me mention the truly ugly or beautiful case, which is the case of trees. In the case of trees, let me give you a definition. A leaf in a tree is called peripheral if there is another leaf which realizes a diameter. For the case where points are on a tree, I need to assume that the predicted point is a peripheral leaf for the result that I announced to hold. However, there are examples in the literature where the optimum point doesn't need to be peripheral. So in a certain sense, putting the condition that the predicted point is peripheral is not necessarily very reasonable, because sometimes the predicted point cannot be optimal, essentially. So this notion of optima for such a problem was studied before in the context of this problem without mechanism design. And then there is a characterization of group strategy mechanisms on trees for the set of points to be the output of a group strategy mechanism for any facility location, not necessarily this one. And it's interesting that the characterization is that a set of points is the output of such a mechanism if there exists a point in a tree at equal distance from all the points in P. So I have a result. It's the same trade-off, but it only works if the predicted point is peripheral. And the algorithm is very similar to what I had before. I start with a predicted point. I take A to be the farthest point from this predicted point, and then I take B to be a farthest point from A in the tree. Of course, if you've seen algorithms and Geeks for Geeks and such, you know that this is a method for computing a diameter in a tree. Take the farthest point from an arbitrary point, and then take the farthest point from the second one, and you get a diameter. Take the middle path on this diameter between the 2 points, and then basically vote for A or B, depending on which side of MAB you are. If you're in a forest containing A, you vote one way. If you're in the forest containing B, you are in a different way. So this is the algorithm. It has to output one of A and B, and that's okay if the predicted point is peripheral. But otherwise, the problem is that it's not clear how close to opt is B. And I don't have a good solution for this, or a good model. My best guess at this moment would be that either do some sort of linear combination of P sub C and B, or using this characterization to do a different algorithm would work. In conclusion, I hope I've convinced you that mechanism design with prediction is an interesting framework. The problem itself is interesting, and it deserves certainly further study than I had time to do. And here is a couple of open questions. I've mentioned the trade-offs for the 3, 4 n-dimensional case. I don't know what's going on there. I don't understand fully what's going on for trees. In the case of dual preferences, remember that the result now had 3 parameters, not 2. Not only consistency and robustness, but also approximate group strategy proofness. So you can probably play with, with 3 parameters and figure out trade-offs, and I don't have anything like that. Finally, this was all about deterministic mechanisms. Now, in the case without predictions, there are randomized algorithms, and I tried to do them, but I got bogged into calculations, and I don't know if you can do this if computations work, in the case with predictions. So that's open. So that's it for me. Hope it was interesting, and I'm waiting for your questions.
Thanks. Let's thank the speaker first, and then we can go for questions.
Thank you, Gabriel.
Thank you.
Questions?
First of all, I suppose like one very obvious extension of this is also the sort of the starting point of my work with Elena on the learning and augmented algorithm paper that we just published. Is there like an obvious way to extend the prediction in your work? It is a point. Is it possible to extend it to something like a fractional distribution of points, or equivalently maybe allow the predictions to be inside the square and its distance to the 4 corners indicate the confidence of where the optimal would be?
Okay, so there are 2 questions here, and the answer to the first one is yes, you can probably do that. I don't know. The question to the second part is, there are very few papers that have done for points inside the square. Probably you might be able to massage some of the results that I have and essentially extended. So maybe the fact that the prediction is not inside might not be necessarily that crucial, because say, for instance, you get a prediction in the square, right? And it's not a corner, but it's close to a corner. Just play the setting where you have as the predictor would be that corner, some sort of like that. And of course, you're going to get some difference, some distance. So for the second part, possible, but I would think that it might just be sloppiness on my side to only work with predictions on the corners.
I see.
Because, as I said, for me, I've only started doing this summer. And during this period, I moved jobs. I started teaching a new course. I bought a house, and I wrote this paper.
Yeah, that's understandable.
So and I've done most of these computations on my own. A few of them I've done.
But anyways, these are good open problems, yeah.
Yes, and I'm happy to send the manuscript to anyone that wants, especially. Maybe I'll wait for the rebuttal to see if there are some obvious problems with the manuscript, and once that is over, I'm happy to to work with people more on this problem, because I'm pretty much doing this on my own, kind of, so I did work a little bit with Cosmin, but now we're no longer in physical contact, and I wasn't able to involve people because I was moving. So I'm pretty happy to work with whoever is interested on this. And by the way, if you look on the mechanism design with prediction webpage, as of now, there are a total of 4 papers about mechanism design with predictions. So there is the paper that at IJCAI that defined the model, and there were 2 papers at EC this year, and the same authors that had the papers at EC have another one on scheduling. So
which is this website?
I think just the algorithms with predictions one.
Yes, on the algorithm predictions, and you look for I don't know, algorithm design or mechanism design or algorithm game theory, one of them, and